Sorry. Yeah. Test. Okay. Thank you. So we talked a bit about VPP this morning, but I realize many people here may not know about VPP. So let me calibrate my presentation. Who in the room knows about VPP? Okay, so some of you know, but not everybody. So what I can do is I can share a few slides about what VPP is, and then while Giles was talking, I did set up a quick container demo using VPP. So perhaps I will be. It's very risky because I just did it now, so we'll see. And maybe we'll have one of those demo effects. And then I will share with you slides explaining how VPP is integrated into OpenStack with this networking VPP ML2 driver. Okay, so let me share a few slides first, quickly, and then we'll go into the demo. Okay, so VPP stands for Vector Packet Processing. It's a project, it's an open source project under Linux Foundation, and it is actually under another umbrella project, which is fd.io, which stands for fastdata.io. VPP is a software that does packet processing. What that means is that reads packet and forwards them and modifies them and forwards them again. So this kind of thing, which is usually done in Linux kernel or in other packet forwarding or in hardware, right? So it's a software implementation. Usually it works on DPDK, but then you have other net packet IOs on top of which it can sit. And this project sits here in the stack. So this morning, Charles was talking about Open Daylight, which is here. I guess later in the day there will be a presentation about OPNFV. So VPP is really low layer, right? The thing reading packet, forwarding packet, and the thing which needs to be really, really fast. So this FIDO project is actually a multi-party project with many people coming from many companies contributing. So we see people from Intel, ARM, Ericsson, so many companies are actually contributors. And it's a very active project, right? So here it's, I won't go into the details, but basically I took 3 projects in the same domain, so OVS, DPDK, and VPP, and try to show the number of commits. So it's a very active project. You have many components, but on that I will go quickly. So that's the thing I'd like. Well, that I will go quickly. Why is VPP fast? And what is that really? Okay. So what VPP does is it reads packets and forwards them. So that does layer 2, layer 3, and now we also have layer 4. What is extremely important to understand is the secret sauce of VPP, and don't tell it because it's a secret sauce. It works with vectors of packets in order to make the best use of instruction cache as well as data cache, right? So what we do is when we have to process a packet, we go through several nodes. So for instance, we can read packet from DPDK, and then we'll get a bunch of packets from DPDK. They will be processed at Ethernet level, and then we perhaps will do IPv6 or IPv4, we do a lookup, and then we'll forward it, right? So we have several steps, right? If you look at the usual code data path, the usual code for data paths, it's actually pretty long, right? So you have a lot of instructions to do because forwarding a packet is not that simple. You may have to do ACLs, you may have to do NAT or not, you may have to do many things, right? So it's a lot of lines of code. And what we are trying to do is to make sure that when we execute an instruction to process a packet, this instruction is actually in the cache of the CPU. So how can we do that? Either we increase the instruction cache size, and I guess our friends from ARM, from Intel, they are all doing that. But what we can do as well is try to be smarter in writing our software. And instead of executing the full processing the full code for every packet and coming back again, what we can do is have small portions of code that are applied to a bunch of packets. So this bunch of packets is actually called a vector. And what we will do is we will execute a limited number of lines of code on this bunch of packets. So with that, we make sure that the code is always, or 99% of the case, the code is in the cache, and then all the packets will take benefit of that, because the penalty to fetch the cache, the code from central memory is actually huge when you are processing millions of packets per second. So that's really what VPP is about. So that's secret sauce number one. Secret sauce number two is, okay, let's assume we are good with our cache for the instruction. We now need to also to make sure that when we are fetching data to process the packets, the data are here as well. So in order to do that, we will process packets with quad loops or dual loops, and I will show you how. So this is a very slow animated slide, so I hate that. So you have your vector of packet which arrives from your NIC card, right, or any other thing. Could be through DPDK. If you have a VM, that can come from a vHost user interface, that can come from regular Linux kernel. And this vector of packet will arrive here. And basically, we'll process this vector of packet. And because we always have we always process a vector, so let's assume we are in this node called IPv6 rewrite. When packet 0 is being processed, probably the code won't be in the cache, because before that, CPU was executing IPv6 lookup, and before that, it was executing IPv6 input. So probably when packet 0 will be processed, there is a very little probability to have the code of IPv6 rewrite in the instruction cache. But now, the beauty of this model is that for packet 1, 2, and 3, they will all have the benefit of the cache warm-up, which was done for packet 0. So that is really one thing which is fundamental in VPP. So if processing this graph is slow, what that means is when we will then come back to the AF packet input or to the DPDK input, we'll probably have a lot of packet waiting to be processed. So what we do in VPP is we tend to measure what is the vector size. So if we have small vectors, that means that VPP is doing nothing because it's processing very small vectors. And when VPP is very, very active, or when there is a lot of packet to be processed, then we'll have long vectors. So the size of vectors is typically between 1 to 256. And if you have 256 vector size, that means that your CPU is under high pressure. If you have small packets, it means that your CPU is doing nothing. So that is what we do to process packets. Of course, you may have vectors that do not go through the same path in this graph. Like here, you have a packet which is an ARP packet. Of course, this packet won't go here. So we are not saying that all packets have to go in the same path in this graph. Okay. One of the beauty of this model as well is these nodes are actually .so file, right? So it's really easy to extend. If one wants to add nodes to do some special processing, I don't know, that may be for ACLs, that can be for whatever you want, it's really easy to extend. You just have to write a node here. You do not modify the rest of the code. So you can localize, have your specific plugin that can be open source or even closed source. You do whatever you want with that. You have your plugins, and you can extend this graph at runtime without having to recompile VPP. So that is something extremely powerful. And you can think about hardware acceleration. Like we see people having NIC cards which are able, or accelerators which are able to do crypto, for instance, in that case, or that can do the first levels of processing in this graph. So of course, vHost user and AF packet input, these are software nodes, but nothing forbids you having cards which will do some level of processing and inject packet later in this processing graph in VPP. Okay, that I will skip. numbers. When I say fast, what do I mean? So just few graphs, and I'm sorry, this is a bit old version, and we can't read anything. Resolution is not good enough. Can you read something? No, it's actually very hard. So trust me. That doesn't work. Can we zoom in? And I will show a live demo, because slides are good, but demo are better. So after that, I prepare kind of a demo, risky demo, but we'll see. What is important here is I did a test with IPv4 and test with IPv6. By the way, we have, with VPP, we have also a testing infrastructure, which is all public. It's called CSIT. It's in the cloud. You can connect to it. It's under the Linux Foundation, and you can rerun the test, read the measurements. All that is public. So what is interesting here is, so we have IPv4 and we have IPv6. And what we did is we increased number of calls, right, to do routing. What routing means? It means three operations, basically. One is receiving packet, two is taking a routing decision, and three is forwarding the packet, right? So with 2 calls, we do like 24 million packets per second, whatever is packet size, right? So that is really good. And one of the beauty of this model is that when you are adding calls, you have a linear increase of the performance with the number of calls. That's extremely powerful, because we did this test from 2 to 36 calls, and we see this linear increase thanks to this cache effect that we are taking. So that is really good. This is with 1 million IPv4 entries. And we have exactly same effect with IPv6, where we are increasing number of calls, and we have this same linear increase, right? Here it's 24 million packets per second on 2 cores, which means 12 million packets per second per core. You seem a bit wake up. 12 million packets per second, right? Thank you, sir. Wow, that's what... 12 million packets per second per core, wow, receiving, routing, and then forwarding. If you do the math, that's not a lot of cycles per packet, right? So that's what we do in this test. And then we did the same for... It sounds like some people are still doing switching in this world. So you have layer 2 processing here, and with layer 2 processing, this is 20 million packets per second per core, with the same linear increase, right? So that is pretty cool. And now it's enough talking. And forgive me if that doesn't work, because I just did this demo before. Here it is. So what I did here is I have 2 containers with an IPv4 address each. IPv4, sorry about that. And what I did is I put VPP to connect those 2 guys, and I will run an iPerf client and an iPerf server between these guys, right? So, and then please help me praying the gods of demo. We'll see whether that will work. So where I'm lost. Okay. So iPerf. 2 regular Linux containers running iPerf. This is not a bare metal server. Actually, this is a VM, right? So I have 2 containers in a VM, okay, running in VMware, if I remember correctly. And these 2 containers can do with a regular TCP connection with VPP in between, like 37 gigabit per 36, 37 gigabit per second. So that's cool. But I told you before, what is actually important is what is the vector size for that, right? So let's have a look at vector size. So we have a magic command for that. So vector size. So these are the nodes in the graph. So you remember the graph. In the graph we have all those nodes, and vector size is 6.93, right, for this tab 0 output. And and for the TX as well. What that means is, the way you have to understand that is, if we come back to this presentation, which was here, when the vector of packet arrives, we typically process 6 packets here, right? That's the average we do, in order to process 40 gigabits per second in regular Linux kernel. Which is fun, is that the bottleneck, when we are only processing 6 packets, that means VPP is not the bottleneck here. What that means is, let's have a look with the bottleneck then. So let me run again this hyperf. And so I don't know if you are familiar with HTOP, but the red is kernel processing. The green is VPP. VPP is in polling mode, so it takes 100% CPU when it has to work, right? So in red, this is the TCP stack. So the TCP stack is actually the bottleneck here. And if I stop my traffic, of course, now everything is at 0. VPP does have this so-called adaptive mode. When there is traffic pressure, it starts polling the packets, right? So it's an active loop. But when there is no longer a lot of traffic pressure, then it stops doing that to avoid burning one core. So that is what is VPP. But this presentation was supposed to be about networking VPP, and I only have 10 minutes. So what I will do now is I will switch to the other presentation, explaining you how that can be integrated into OpenStack. Because all that is useless if that is not integrated somewhere. Okay. Okay. So networking VPP is an ML2 driver for OpenStack. It was primarily designed to support NFV, right, at the beginning. What are the OpenStack features we support with VPP? VLAN, VXLAN. VM connectivity is only with vHost user interface, otherwise that's too slow. We support many security features, including regular OpenStack stuff, such as security groups, but very advanced stuff, such as JSON Web Token with certificates. I will show you what that means. And we do layer 2 and layer 3 with HA and all those stuffs. So networking VPP has this architecture. It's etcd-centric. What that means is when Neutron have to create a port, instead of communicating directly with the compute nodes, what it does is it will put that in etcd, and then the compute nodes will wake up and will take into account that stuff. That is really cool, because the problem with OpenStack in such a distributed system is you don't know when a failure will arrive, but a failure will arrive at some point. And what we are doing here is we are making sure that when, let's assume Neutron wants to create a port on this VM, okay, on this compute node. If this compute node is dead for some reason, or rebooting or whatever you want, when it will restart, it will actually fetch the states from etcd instead of reading them from Neutron. So it's kind of intent-based networking, if you will, because Neutron is writing its intent, the desired states, in etcd, and then the compute nodes are actually reading those desired states. And if the agent, so let me show you what that means. So typically creating a port will go through these several steps. So first, there is Neutron asking to create a port. Then this is stored in etcd. Later, that will be understood by the agent. And then the agent will send the feedback and will notify Neutron so that the VM can be created. If for some reasons the agent crashes, what it will do when it will restart, it will do what we call state reconciliation. What that means is every object within VPP comes with a unique ID. And when we restart, this agent will actually fetch the state from etcd, fetch the states from from VPP, and we'll reconciliate we'll do a diff between those guys and remove states which are useless now and include new states which are required. So that is something interesting. Other interesting thing is it's very much etcd centric, which means that if for some reasons etcd fails, there is another one which can hand over. There are many cool features with networking VPP. One of them is now we have this redundancy between layer 3 routers based on keep alive D. So if one dies, then the other one can hand over. So that's also extremely useful in production. Security, we have role-based access control. So when only few the compute nodes comes with writes, and you cannot write and read anything in etcd. So basically, if there is a malicious compute node for some reasons, then you are sure that the database cannot be overwritten by someone who doesn't have the rights. So that is another cool feature. We have these JSON web tokens that can make sure that the states which are written in the database have been written by the right compute node. So we have all that, right? So I will just go to the roadmap slide. We now have a lot of features. The next thing we need to work on is this VLAN-aware VMs that we don't have, and have a better ARP handling for v6. So these are really the remaining features we have now, and you are more than welcome to contribute or to test it if you want. I realize I may no longer have time, so do we have time for questions? Or okay.
Yep, 5 minutes until the start of the next presentation. Before questions, I'd just like to, for those who aren't on the mailing list, we're having a gathering. There's some space in the Mancampus Cafe later this evening from 7:30. So you're all, well, some of you are welcome to join us. Come along. If there's room, there's room, and if there isn't room, then it's also the central part of town. So it's a big enough place. We should be able to fit a good number of us in. With that, any questions about VPP?
VPP or VPP used to connect containers or for OpenStack? I know it was a lot of things being showed in this presentation.
There is another VPP presentation later, which will go into more detail, I think, in the yes. Higher level technical details of VPP. Anybody have any questions?
Okay.
You shout it out. Jerome, can you repeat the question for the... Fuzzy?
I'm wondering, is the agent of VPP replace the agent of the Neutron on compute nodes?
There is...
so the question, just for the recording, the question was, does the agent of VPP replace the agent of Neutron on the compute nodes?
I will answer. So there is there is not an agent for a neutron. In general, people may use the agent which is on the compute node will depend on the virtual switch you will use, right? So if you are OVS, you will get a neutron agent. If you are using a regular Linux bridge, you will use another agent. So we have written an agent which is running on the compute node, and that will drive VPP. So yes, the agent on the compute node replaces this agent, because this agent knows how to talk to VPP and knows how to talk to etcd.
I actually have a question as well.
Go.
Is this different from the Honeycomb agent?
It is, absolutely. Okay. Honeycomb is a netconfig agent, and here it's an etcd thing, right? So this one is written in Python.
You said VPP run mostly on top of DPDK. I know there is also an option to run on top of ODP. Please, can you explain the benefit?
Sure. So in the past, VPP was tightly coupled with DPDK, and during the last version, what we did is trying to have DPDK being a plugin, an important plugin, but just a plugin beside others. So there are many reasons why not using DPDK. So for instance, in the demo I was showing before, I was connecting regular containers, which doesn't work with DPDK. So So on ODP, right now, I don't know, to be honest with you, because I have not done a lot of tests with it, but I know people who are using with it, are working with it. So I guess there may be some better performance with some NIC cards, but I'm not too sure about that, so I don't want to answer.
So last question. Anybody else have a question? I'll go beyond the usual suspects. Yeah.
Can you use VPP agent and compute nodes together with, let's say, OpenStack agent?
So the question was, can you use the VPP agent along with the
I think
the Open Daylight?
OpenStack enables this option to have hierarchical drivers, so I don't see good reasons why that wouldn't work, but I don't really see the benefit of doing such a thing, right? So in theory, yes, but why would you do that? I mean, if you use one forwarder, it's probably for a good reason. So I don't see why you would have those two guys collaborate.
Was that alongside, just again for the recording, the VPP agent alongside the OVSML2 agent? Okay, well, or another custom agent.
Yeah,
you might mix SOIOV
I've
and
never seen
VPP
that.
perhaps?
It looks to me a bit like a Frankenstein solution, but why not? Why not?
Okay, we're out of time. So thank you very much, Sean.
Thank you.
So my next speakers, I will be meeting them for the first time on the stage. So Javier Marcial.